All right, we will go ahead and get started. So welcome to the 21st session of EE 7391, 5391. So I'm back. It's a pleasure to be back. And in fact, as I adjust this, thank you very much for allowing me to go to my conference. I guess I wanted to say a little bit about it because I appreciate the opportunity to go. This is where I was. I was at the Asilomar Conference on Signal Systems and Computers. This is actually I believe it's the 52nd version of this. And I've been to, actually, I checked, I've been to several of these. I've been to, I think, 18 over the years. And I went to, let's see, this is the 52nd. I think I went to the 23rd. So that tells you it's been almost 30 years of attendance on my part. Although, like I said, I haven't attended every one. There was actually, what do you say? There's program, obviously, but there was a section on adaptive systems, machine learning, data analytics. So this part is actually something that's been recently introduced, and in fact, this caused this particular conference to have more submissions. I think it had the record number of submissions. But it's on the West Coast, and like I said, you know, it is in a nice place. This is near Monterey, about 400 yards that way. From this building is the beach, although it's kind of cold, and I was only there 15 minutes. I felt I had to go since I was there near the beach. I should at least be on the beach for 15 minutes. But I spent most of my time in sessions talking to people. And like I said, this is one that tends to get participation from the West Coast, but it also has international participation. Met folks from Germany and from China and other places. Youngest attendee I met was probably 23. The oldest I knew is over 80. So it's quite a range of folks, mainly in signal processing. But like I said, it's some also people, computational biologists, those sorts of people. I was actually presenting something at a poster, and a person from a company named after a fruit said, "Good stuff." And there's folks from Amazon there too, and Sonos and audio processing folks. So it was good. It was very useful, and like I said, and I guess I should mention, there's stuff that I learned here too, which is very important. In fact, I should probably mention that. I'm going to try to dig this up so that we can actually talk more about this. There was actually sessions, or a session on non-convex cost functions and performance bounds. And it turns out this stuff applies directly to, you know, deep neural networks, basically what we're talking about in this class in terms of machine learning. One of the things that was interesting, though, was that there was actually a result which talked about generalization performance. Generalization performance, which we're going to talk about what generalization performance is. Actually, I think we already have to some degree. This has to do with, you know, on patterns not seen, right? This is really what we're trying to figure out. We're trying to figure out how well a system works. And this turns out to be proportional to something which is akin to 1 over the number of training patterns so as you increase the training patterns, I should say generalization performance. I have to fix that. It's actually generalization error is what I want to say. Generalization error. So generalization error on patterns not seen is proportional to sort of 1 over the number of training patterns. So the more training patterns you have, the better generalization error you have, which is reasonable. And then plus another term which is actually linearly growing, which is sort of the number of times the training patterns are used. Okay, kind of, you know, and there's obviously a constant here. There's some K2 here and K1 there. And this is interesting. This is actually saying if you use your training patterns too much, then you get a linear growth in the generalization error because you're effectively overfitting, right? You're trying to design a system where you're using the training patterns too much. But of course, you need to use the training patterns to reduce, the number of training patterns helps you to reduce this. So the goal is, if you can do it, is to use each training pattern once and get the most out of it. Because if you can do that, then you get the minimal impact of the second term. And of course, you take advantage of using a training pattern to reduce the first term, right? And that's kind of cool, actually. I think this is really useful. And in fact, I'm kind of reminded of something. I'm actually reminded of, you remember this analysis business that we did way back when we talked about how we had non-stationarity, right? Non-stationarity in mean square analysis, and we said, you know what? When things start wandering, you have two terms, and there's one term which goes down, and there's one term which goes up. The term that tends to go down is one that's driven by kind of your step size, and then the one that goes up is driven by 1 over your step size. And it's kind of, so it's sort of, again, similar sorts of ideas. And by the way, the scaling factors K1 and K2 are both reduced when you lower the step size. That's the other piece. In other words, train slow. But of course, the problem with training slow is you're not going to use your patterns that much, so you may need to revisit your patterns, which means you're increasing the second term. So, and anyway, it's interesting. I think, like I said, there's stuff happening in the field which is starting to help us figure out how to kind of how to bound and understand how these overall systems work. And I think that's the exciting part. So that's one of the reasons why we go. Yes?
So what do you mean by generalization error?
Generalization error. So the idea here, and this is actually related to today's topic. So this kind of takes me into the discussion that I wanted to have today, which really has to do with. So generalization error is going to be discussed in the context of what we were talking about last time. So if we recall last time, what we were talking about were kind of weight constraints, regularization, and sharing. And what I mean by this is all these terms are joined. Weight constraints, weight regularization, if you will, and weight sharing are kind of the ideas here. And what the issue is, the general issue that we have is that multi-layer neural networks are over-parameterized. And what this means is that there is a risk of overfitting. So what I mean is, it's kind of along the lines of what I talked about last time, where I said we have the training error, we have J of K, and we have, this is an error, and it goes down with training, sort of iteration number, iteration K, and it goes down. But then the issue is the test error, which is the performance, goes something like this, and then can actually start going up. So this is the test error, and this is the training error. And if you will, good generalization is equivalent to low test error, on patterns not yet seen. So that's what it means. Generalization can be thought of as the property of how well something works on things it hasn't seen, and good generalization means a low test error on those things. And generally we want to do this, and that was the motivation for kind of early stopping, right? We talked about that as one of the methods. And so one of the methods to deal with this is early stopping. And again, this is from last time. And actually it's interesting, we can view early stopping as actually a type of weight constraint. What we're saying is it's actually a simple weight constraint. And the simple weight constraint says that limits, if you will, the weights Wm and B of m to not move too far from their initial values, right? What we're really saying is if we think the initial values have value, then we shouldn't be too far away from them. And therefore, if we're going to stop early, we're saying let's not let the Wm get too far from its original value and the Bm to get too far away from its original value. And that is, basically what we try to do. This is basically not to let them to move too far over the course of training. So this is what we want. But this gets us to an idea that we're actually going to do a little bit better in terms of constraints. And let's actually talk about weight regularization. Now, what regularization is for weights, it's actually a modification. We're going to modify J sub k so that, if you will, the weights are not too far away from zero values. So what we're basically saying is, kind of the origin in weight space. So the idea here is we're going to say, okay, let's try to constrain the weights so that when we optimize the cost function, they don't move too far away. They don't get too large, as it were. And the basic idea is to augment the cost. So we have an augmented cost. And this augmented cost is J sub k is equal to this new cost, is the original cost, say the mean squared error cost or the cross entropy loss, something like this, plus another weight, which we're going to call lambda. We're going to divide it by 2. And then we're going to sum across all I, j, and m, sort of wi, j, m, the weights for the mth layer, the ijth weight squared, plus the sum over all im, b, I, m, k squared. So we're going to let that be another term. And this is our constraint term that, of course, if it's minimized, it means that the weights are 0. So minimization means basically wi, j, m, k equals 0 and b, I, m equals 0, which of course we don't want. These will mean wi, j, m, k won't be 0, right? Because we're trying to minimize that. That'll drive the weights away. But clearly this is a balancing between these two things. Now, to understand this, it actually helps to go back to the adaptive filtering context. So we're going to consider adaptive filters for a moment and understand this. The equivalent method, which we haven't talked about, would be the scenario where, in this case, we call it J sub n. This is 1/2, E of n squared plus lambda over 2. In this case, we just have the weight vector, the Euclidean norm of the weight vector. Euclidean norm. And so this is how we set this problem up for the adaptive filters problem. And of course, E of n is just the desired signal minus the weights transpose times the data. And then we do the same thing. We let Wn plus 1 get W of n minus, say, mu over 2 partial j with respect to W. And when you go through and do the math, substitute this in, what you end up with is an algorithm which looks like this. It's equal to 1 minus mu lambda times W of n plus mu E of n x of n. And so what we have is the standard gradient showing up here, and then this value is slightly less than 1. And of course, slightly less than 1 times W means the value starts to decay away. So rather than using a W of n, which is just accumulating these gradients, we sort of weight the previous value of W by small values to shrink it, if you will, reduce it slowly to 0. And if there were no terms driving it, then the weights would go to 0. But then the gradient terms cause the weights to not be 0. And these two terms kind of, if you will, you can think of them as kind of fighting each other in some way, right? Because these weights are trying to go to 0. This attempts to make, W of n actually approach the 0 vector. But of course, this is going to minimize. We want this to be basically W of n approach, an Rx x inverse times P dx. So we're getting a balance in between those, okay? But it affects the dynamics. It affects the way this thing adapts. And you can show in adaptive filters this lowers performance. This is the reason why people don't do it. I mean, it's not really something that tends to happen because you want to minimize this and come up with the optimum solution. You don't want to try to move the weights down, and it's due to the fact that basically the system modeling is limited, right? It's a linear system. It has a certain number of parameters. It basically runs into a scenario where you're actually limiting the performance of the system because you don't have enough degrees of freedom in the weights, okay? I should say it generally lowers performance, but it can be useful in scenarios. This is the only place where it's potentially where it turns out lambda min of Rxx is very close to 0. So if you have a minimum eigenvalue, then it turns out the inverse matrix, when this is true, this tends to make Rxx inverse, has large entries. Right? So if you will, W of n could be very large, but it turns out, the minimum eigenvalues tend not to, the actual cost function in those dimensions don't really matter all that much. So in some sense, you get weight growth without any benefit in reducing cost in terms of the overall performance. So it can be useful in that scenario, but it generally isn't used that often. Usually when you have these scenarios, it's due to things like numerical errors, which you try to solve other ways. In other words, you try not to use this. This is somewhat of what might be thought of as a sledgehammer approach, where you probably want to be a little more nuanced in your numerics in terms of how you deal with it. But you can show in adaptive filters, it's not something that we tend to do, but in neural networks, basically the fact that there is finite data, basically there is finite training data, that training data is finite, that is, n does not go to infinity, means that this can affect generalization performance. So it is a way to allow us to essentially control the ability of the system to actually calculate good answers for data it hasn't seen based upon a finite data set, okay? And that's one of the reasons. And the other issue that's important here is that, basically NNs are more capable at modeling. So we have, if you will, more degrees of freedom to play with. So that's the reason why this particular approach tends to be very useful. And so what it means is that this is a useful change that people use. You'll see this. It's sometimes referred to as L2 regularization. It's also called L2 regularization. So you'll see that in papers. People say, yeah, we use L2 regularization. That's what they're doing. They're basically doing this weight decay business. And the way it shows up is in the algorithm, sort of backprop. What we have is WMK plus 1 gets 1 minus eta lambda, because we now use eta instead of mu, times WMK plus eta times the standard backprop term. And we've already done this for this particular set of weights. You know, it has to do with derivatives of the output nonlinearities, as well as the weights themselves, the transpose weight matrices, and then the error vector associated with the calculation of the cost function. And we've already talked about that. So you basically just alter it, and same thing for the BM sub k plus 1. So you do it for the bias weights too. Now, the issue that we have is, you know, again, we have a standard term that we're going to put in here. Of course, the issue is how to choose lambda, okay? Right? Yet another parameter to pick. So you're saying, okay, well, I'm going to choose lambda. I got to make a choice in C. So it ends up being another sort of issue of, okay, well, I have another parameter to play with. Maybe I can get better performance, but I might have to do, you know, several simulation runs and then alter the parameters associated with those simulation runs. So it just creates more, if you will, things to experiment with. But it tends to provide an improvement in performance, or at least an ability to improve performance when you use it. So it's something that we consider using. But again, having said that, you know, it's not as if we've somehow derived the fact that, you know, driving weights to zero is a good thing. We haven't really derived that. All we've simply said is, and in fact, it used to be that the concern was the weights would get too large and that would cause, you know, output nonlinearities to saturate and, you know, other issues to show up. We generally don't have that problem anymore. We're able to deal with that by proper choice of nonlinearity, proper initialization. We kind of put the weights in the right place. So that's no longer a problem. So in some sense, you know, some of these things are also leftover vestiges of things that people did to solve other problems. So I just want to point that out. Any questions on this? Like I said, it's pretty straightforward. And, you know, like I said, it makes sense to do some form of smoothing. You could think of this as well as smoothing of your weight trajectories, right? You're taking your weights and rather than just accumulating the gradients, you're kind of filtering them with a first order, you know, or leaky integrator as opposed to a straight integrator. So it's that kind of idea, okay? But it is a weight constraint, and it's important to talk about it that way. There is another type of weight constraint which actually comes about through another concept, which actually, again, seems somewhat strange to us in terms of signal processing side of things, but it's to introduce noise into the adaptation process. Now, I know you're thinking, well, that seems odd because normally we try to get very clean signals. So why is it that I would want to introduce noise into the adaptation process? Well, there's actually a motivation that we can think about. Again, we're going to go back to, we're going to consider the adaptive filtering case because, again, it gives us sort of the insight to understand this. Suppose I have an input signal x of n, and I have my adaptive filter, which again has a weight vector w of n. But before I allow that weight vector to act on the signal, I actually add noise here. I'm going to put some noise here. And we're going to give it some variance, sigma I squared. So I introduce noise at the input of the system. And I know you're thinking, well, why would I do that? Seems kind of odd, but let's do that. If we do that, then here we're going to end up with some d hat. It's going to have some of that noise as input to the system, okay? And then, of course, we're going to have a d of n over here, which we're calling y of n now in the context of training neural networks. But then we do this. We have a minus and a plus. We have an error. We adjust. Okay. Now, obviously, this error basically includes a noise component from the introduction of noise at input. Now, if you do this and you say, okay, let me just do it and see what happens. If you do an analysis, it's pretty straightforward to see that the expected value of, and basically, now, and I run LMS. I'll let LMS run on this thing, standard gradient descent. If I do LMS on this, it turns out that what I get is something that looks like this. It's kind of interesting. I get 1 minus mu r. Actually, what I can say is, what I get is 1 minus mu times sigma I squared times identity, expected value of W, plus mu times the expected value E of n, x of n, which of course is just the gradient. Now, this should look familiar. It's just what we talked about, right? I mean, it literally is, this is like lambda in weight decay, right? What we just talked about. So in some sense, what we're doing, if we add noise to the input, what we're doing is actually creating, and of course we can just make these ones, 1 minus mu sigma I squared. We're effectively doing like weight decay. So this is not a crazy idea, at least from the standpoint of adapting the coefficients. Now, the reason why adaptive filtering folks don't do it is because now d hat sub n is noisy. So I have to actually compensate or remove this noise somehow from my output to really make good use of either d hat of n or even e of n. So I wouldn't want to do that. But clearly, it may change the way the dynamics of this adaptive filter are working, and it may help me. And in fact, you could even think of it as improving convergence performance, right? Because I'm effectively changing the covariance structure of the matrices that are showing up, right? So it's kind of, it's kind of interesting that way that we end up getting this type of behavior with adding noise. But if you will, the idea here is to perturb the network or system in a structured way. And basically what we're trying to do here is we're trying to increase robustness. So we're trying to make the system more robust. We're trying to decrease any dependence on, specific training signals. So if we have specific training samples, i.e. improve generalization, right? This is obviously something we like to do. And we can do that if we introduce or we perturb the network in some way, then we can introduce these types of changes that should make the system more robust to any specific data that we might have in X, Y pairs that we're using to train this thing. Okay. Very important concept that's been developed associated with this. And the mechanism is called dropout. Okay. It's introduced by Srivastava et al., actually, along with Hinton and other folks. I'll show you the paper in a moment. And that's in 2014 is when this came out. It's actually a simple way to introduce, and it turns out it's multiplicative noise. into basically a neural network architecture. Now, what do I mean by multiplicative noise? Well, this is a concept, again, you won't find this description, you won't find this description anywhere else. It's because people don't necessarily think of it this way. They tend to think of it as, oh yeah, it's doing some, it's averaging networks and so on. Well, no, really what it's doing is introducing multiplicative noise because we understand what this means. What is multiplicative noise? Well, multiplicative noise is where essentially you have a signal x of n, and rather than add, you multiply by a g of n. And this is also noise. Okay? So if you will, y of n, again, this is not the x and y of training, but just input, output. Y of n is g of n times x of n, where g of n is basically a noisy gain sequence. And of course, if it's a noisy gain sequence, it has some g naught, some average value, plus some delta g of n, right? Some variation. So here's the average, and this is the variation, right? And that's what it's doing. And now, if I think about what y is, that implies y is g naught x of n plus delta g of n times x of n. Now, here's the thing. The statistics of this, by the way, this turns it into an additive noise model, right? This is like an additive noise. I'm taking x, if I make g naught close to 1, then y is x plus some noise. So I've made a multiplicative thing into an additive thing with this model. But the statistics of this model of this additive noise depend on x of n, right? It depends upon the input signal. But in particular, if x of n is small, the noise is small too. That's really clever. I mean, if you think about what that means, what it means is I'm perturbing the system if I multiply by noise. But I perturb it in a way that allows me to kind of be robust to changes in my input value. Because my inputs are going to be big and small, right? I might have a really big input, I might have a really small input. If I add noise, then the additive piece starts dwarfing the small values, right? But if I multiply, then the multiplicative noise scales with that. So it's kind of like the SNR is kind of better behaved for this model than it is for the additive model, right? You get the idea? So small patterns, for example, small elements within patterns are not going to get dwarfed by noise if you multiply. So you kind of get this really nice, if you will, scaling associated with this type of perturbation. So that's the real reason why this sort of behavior is very useful. Now, how is it that you actually do this dropout? What's the mechanism for doing this? To implement dropout, you essentially randomly remove nodes from the neural network during training. And you do this with a probability 1 minus p, or equivalently keep p per, p fraction of nodes, right? So the idea here is, oh, by the way, this is one step. Maybe I'll say both steps. And then the second step is, this is during training. And then during testing or operation, so after you've trained and you're testing or operating, you essentially multiply all weights by P. So the idea here is you would take Wm of k and you would say P times Wm of k. And you would say Bm of k. Those weights would get P times Bm k. That's what you do. So you have to scale back the weights, and we'll explain why in a moment. But the basic idea here is, so this is the paper. The basic idea here is I start with a fully connected network, but during training I start dropping nodes. And they actually talk about dropping, say 20% of the nodes to 50% of the nodes. So you might think this is quite a bit, right? To actually drop the nodes. And then after you do this, what you do is at training time you have the weights, but then because you're presenting the data with a probability P, at test time, what you need to do is, these are always present now, so now you need to decrease the weight strengths by a factor P. So if you will, the training kind of, gooses your weights, causes your weights to be larger than they need to be because there's fewer connections. And so they're getting, if you will, those connections that are remaining are getting trained more significantly. So in order to deal with that, you then adjust the values by P times W, P times the bias, okay? And you're saying, how important is this? Well, it turns out this is just like, I don't know, it's like salt on food. It works so well. This is a sort of thing where, applying it to methods, the test error without dropout is up here, and with dropout it goes down further, right? And in fact, what they find is that with dropout, there's really, you can kind of just continually train and you don't have to stop because the dropout, the nature of the dropout's actually causing, if you will, appropriate regularization of the weights. And these are for systems that have very, very large numbers of parameters. This network has more than 65 million parameters, okay? So they're running into scenarios where they have a huge number of weights. And this is performing a form of regularization so that just, the fact you have all those weights is not a problem. It's actually, if you will, constraining the overall adaptation. And, they have, again, test performance and metrics and so on. Where's the one I want to look at? I think I want to talk about, they do actually apply to MNIST. Here's the MNIST. And this is a fully connected MNIST solution. It's not a convoluted neural network or any other constrained system. But a standard neural network gets about 1.6% error. When you start adding dropout, then you're getting this down to on the order of 0.95 or 0.94, right? In terms of being able, so you're able to reduce the error by quite a bit. It's not quite a factor of 2, but it's quite good. And then I think some of the best performance has gotten down to even half of this. So this is, if you will, not making changes in the way the system is interconnected, not really changing the layers as it were, but just simply allowing a system to have adaptation and then using this way to regularize the resulting weights, and it has better performance. And I've seen this as well. I've actually experimented with this a bit myself. It is the case that dropout tends to help. One of the things also that happens, and you can kind of see this in one of the other things that they talk about in this paper, these are actually features that are learned on NIST. Without dropout, these are kind of, the way to think of this is these are, intermediate images that are created within the network. The intermediate images tend to be noisy and they tend to have features, energy that's spread out, whereas the, dropout with P equal to a half, so this is dropping half of the nodes, starts to create smooth features within the network, smooth patterns. And yet these patterns have different, if you will, shapes to them or different indications. So you can kind of see, they actually are kind of grabbing different pieces of the image puzzle to kind of characterize and then be able to use these in constructive ways for classification. So this is also something that we would say is a good thing, because again, smoothness and being able to see some structure in this indicates that there's some benefit to being able to impose this, and it also suggests that it's regularization, right? Because regularization implies smoothness, and this is an indication of smoothness. So this is showing you sort of the overall characteristic and behavior of that. But notice here, they're actually using, comparison of different regularization. Here they have L2, that's that weight decay. Well, here is dropout plus L2, so they used both, right? So now we're starting to mix both dropout and weight decay. So you get the idea. You wouldn't necessarily just use this in place of weight decay. You actually would use it with weight decay as well. So that shows you, the overall types of things that you can get with this. And they apply it to other methods as well. Oh, here's the other thing. If your data set, this is actually effective varying data set size. With dropout, it's actually kind of hard to see. With dropouts, this one, it starts, if you have a small data size, then dropout doesn't help. If you have a larger data size, more data points to train on, then eventually dropout beats performance without dropout. But then as you increase the training size, then the difference, dropout's still better, but the difference between these two gets smaller. So if you have a large data set, then dropout will be diminishing, right? Diminishing returns on this. So there seems to be some kind of intermediate point having to do with network size, data size, in terms of training data set size, and this dropout business to be able to get you a benefit. But, like I said, it's diminishing returns. But notice, it's always lower. So the dropout performance beyond a certain point always gives you better performance. Or dropout always seems to give you better performance. So it seems like something you'd want to do. So it has become an important feature in a lot of training algorithms and kind of, brought to bear on a lot of different problems. People tend to use it. And so you'll see lots of people saying, yeah, I have this new architecture. With dropout, it does this. And so they'll just, use this. And like I said, it's a fairly simple modification of a technique. It's easily understood from the standpoint of this being able to drop nodes and then this being able to scale the weights. Any questions on that? All right, we'll go ahead and pause here. It's a good pause point, and we will pick it up next time. Actually, the one thing I will say, I'll come back, we will say something about how this relates to multiplicative noise, because it does. So we'll give you that after the break. We'll see you in about 5 minutes. Around 5:49. right, let's continue on. So I guess I wanted to also make a mention. So as I know, I saw you on Friday last week. Thank you very much for turning in your homework. We do have more homeworks coming. I didn't bring one today, but we will have one assigned this week. It'll be either tomorrow or Wednesday. We're going to have you implement convolutional neural network, as it turns out, because I think it's important to do it. We're going to simplify it, though, so that you're not wrestling too much with indexing, because that's the hard part in building the code. But you're going to. I want you to see, the ability, basically the structure of these types of systems. But we're going to have 2 more homeworks, as it turns out, due. And in fact, there's going to be a last homework as well on sort of principal component, independent component analysis stuff, which is an important piece. We'll talk about that towards the tail end of the class. That's going to wrap up the class as well as other topics. But I wanted to mention that to you to keep your eye out for it. And we'll make that due in class so you don't have to come to meet me outside of class. But like I said, I appreciate having the opportunity to go to conferences. Let's talk about this issue of multiplicative noise. And obviously, actually, I should say the result of dropout is it improves basically generalization, which again could be thought of as testing performance. So, when you actually run the system on patterns the system hasn't seen, then it tends to work pretty well. And here's the basic idea. Dropout can be thought of as a time-varying nonlinearity okay, and it's a time, because it happens on the nodes, right? So it's a time-varying nonlinearity if I take FIM of d hat, right, whatever that is, whatever that d hat of nk, I guess it could be a vector value. It's like g, actually I should say, the new nonlinearity is like GIM, a noisy value, times the original FIM d hat, right? So we're taking the value and we're multiplying this, and this is either basically 0 or 1 with probability, 1 minus p and p. So you can think of it as, that's like a binary multiplicative noise, right? Binary O1 multiplicative noise, right? So, and by the way, why does that show up? Because, we've got these nodes, right? We've got this thing, we've got this node, we've got the F, we got the G, multiply by GIM, right, of N. Actually, now I think about it, it's GIM of N, but it's applied to different patterns. So it's actually, now that I think about it, it's actually different for different patterns and training points. So it's going to be that. So we're actually going to change it both for N and for K, for the training patterns and for the weight updates, because we're going to randomly do it as we change the weights. So it's GIM and K to kind of create this noisy output. And of course, this becomes sort of the XM plus 1 value, right? IM plus 1 NK value. So this is the next layer's input. So that's the reason why it's noisy, right? We have these inputs coming in, we've got the nonlinearity, we multiply by binary 0 or 1, but it's noisy, and then we get the output. So it's exactly like this idea. So we could think that, we're kind of leveraging the fact that the presence or absence of patterns is kind of modulating this resulting noise. But it's even better than that. If you actually go to the paper and look at what they talked about, they said, we use this binary noise to say, it's kind of like using multiplicative noise. But go to the section before the conclusion, and they say dropout involves multiplying hidden, activations by Bernoulli distributed, and they said, we could also do Gaussian, and this works just as well or perhaps better than using Bernoulli noise. So using Gaussian instead of the Bernoulli might even provide a performance advantage, right? And they say, okay, we're going to perturb the hidden activation by some Gaussian values, and then we describe this, and okay, well, let's make the Gaussian, we can make it binary, and then, the variance is like this, so we can match the Gaussian. And then they said, they could be set up so that the random variable being multiplied has the same mean and variance. Both of these extremes work well, although preliminary experimental results suggest that the high entropy case, which is Gaussian, works slightly better. But yet they don't use it. It's kind of odd. I would think that, this is what I would call my dropout. It may be due to the fact that Gaussian is kind of painful to make in some places, whereas binary is not. Did you have a comment? Yes.
So, for the binary case, at least we can say that we are dropping few nodes. What would a Gaussian mean? Like you're scaling it by some weight? Is that?
Yeah. Well, in this case, you'd be scaling it. And by the way, I think you'd actually probably want to scale it with a Gaussian weight that's positive. Although it probably doesn't matter all that much, but I would think that you'd basically say make it a variable gain. You're right. It's sort of saying, well, what is the interpretation of this? Well, it's maybe harder to interpret, but the fact that it is multiplicative noise means that the design of the noise distribution is open, right? So the fact that it may not fit the interpretation of what they're talking about, which is kind of averaging different different networks that have different configurations. It's more like, this multiplicative noise thing means that, so we have an interpretation issue. But they're not using that interpretation to improve their method, right? So in some sense, I think this is, this is, let's put it this way, potential opportunity. Maybe we could do better with Gaussian. And by the way, if I was looking at this problem and I wanted to have maximum entropy, i.e. the most bang for my buck in terms of a distribution, Gaussian's it. Because Gaussian is the maximum entropy distribution. It is the one that introduces the largest change for the littlest effort, as it were. Might enable me to lower the variance, for example, to adjust the dropout rate would be the point. But they've kind of left it open. I think this is kind of a, looking back at this comment, this is a paper that came out, 2014. So I don't think people have really tracked this down. This is probably a loose end. People need to kind of explore. But that shows you an issue that, potentially could be looked at. So this is pointing out to, again, another important area that I think is useful, another important feature that people tend to use. And like I said, you'll see this show up in a lot of papers. So we've talked about sort of, early stopping. We've talked about weight regularization. Dropout's an example of that. Let's talk about sort of the third issue that's important here. So I guess I'll make a mention, maybe, normal here works better. So we'll kind of put that out there. So maybe to look at some other point in time. Let's talk about the third issue, which turns out to be also very, very important, which is weight sharing. Now, it turns out weight sharing is an old idea. It's basically you reduce the number of unique weights weight values in the neural network by setting some equal to others. Now, it turns out that this is also an old concept. And I say it's an old concept because it's shown up in adaptive filters. And again, this is going to be my thing. People might say, well, wait a second, where does all these ideas come from? Well, it comes from, people are borrowing, right? They're coming up with these ideas, which is essentially, using weights multiple times is important to obtain, structured solutions. And a good example of this, and we kind of actually had this, I should say, this idea sort of showed up in one of your exam questions, as it turns out, your midterm exam. Linear phase filters. Okay, what are linear phase filters? Well, generally these are devices that delay sine waves equally. So the idea here is if I have some pattern that's like this, this signal, say this is x of n, and it goes through a linear phase system, okay? Well, actually, maybe I'll rather than do that, I think it's better if I actually do it in terms of sine waves. If I have a sine wave, so I have a sine wave of a given frequency plus another sine wave of a different frequency, and they start at specific times, okay, and I send it through a linear phase filter, then what happens is the output signal, obviously the sine waves could have different sizes, but it turns out they have a delay. There's essentially a delay, a group delay, which causes this point to actually be at the same point here. All right, again, it might be a different size, but basically it's gonna have that shape, and then this guy is gonna start here. So basically, the group delay is constant. So it tends to preserve shapes. That's the way to think of it. This type of filter preserves shapes. Preserves shapes of signals. And of course, that's useful, especially when you might be sensitive to that. For example, if you don't do this with audio signals, then suddenly you have echoes, and you don't want them, right? Because you want the signals to come in at the same time. And you don't want the high frequencies to be delayed with respect to the low frequencies and vice versa. So the point is you delay them in the same amount, it works out. Well, the easiest way, there's a simple way to do this. The simple way to design an adaptive filter to do this, and the way you do it is what you do is you basically make the first half of the weights, W0, W1, you go up to WL over 2, and then you go WL over 2, WL over 2 minus 1, all the way down to W0 again. So you basically make this thing symmetric. Symmetric in terms of its impulse response. And if you do that, if you set your W of n equal to that, then you can adapt these coefficients. You only have L over 2 coefficients, or L over 2, I guess, minus 1. You have basically L over 2 coefficients that you adapt, and then the other ones you copy. And this also saves you work, right? It'll save you the time of adapting, but of course, the time to the time to actually compute is not too bad here. L is not generally that large, it's not that big of a deal. But it is a way to basically reduce the number of weights. And so this is weight share. This is using the same weights in two different places. Well, that's what happens in a class of neural networks. This is used in what's called a convolutional layer within a neural network. And these are then known as convolutional neural networks. And you'll see this all over the place. You say, yeah, I used a convolutional neural network. All they're really saying is they've used a convolutional layer within a neural network. But it's not this linear phase stuff. So maybe I should say it does use weight sharing, but it's not linear phase. Let's talk about what it actually is, okay? Well, it's doing convolution, okay? So let's recall, and by the way, we do have this in adaptive filters, we do convolutions. We compute convolution. right? And the reason why is because what is a convolution? Well, that's d hat of n. It's the sum I from 0 to L minus 1, W of I times x of n minus I. So this operation is called a convolution. Okay? And the way to think of it is a weighted combination of samples indexed by time or space, where the weights move across the signal, right? So the idea here is I've got these weights, I've got time domain samples, x0, I guess I'll start with x1 maybe. Don't need to use x0 here. I have x1, x2, x3, and I have these weights, and I'm, multiplying the weights. In this case, I have, well, and here I'm going to change my notation a little bit. I'm actually going to replace this with I from 1 to L, Wi times x n plus I minus 1. So I'm going to reverse the plus to minus. Now, I know this is actually a correlation. So you guys will say, it's not a convolution, it's correlation. Yes, that's true. But we don't care about that. We don't care about the time reversal business. I mean, we're not taking Fourier transforms. So, the real math, where that math would matter would be in the complex domain if we were doing transform-based calculations. We're not doing it. We're doing direct form. So correlations, convolutions, they're basically equivalent. It's just basically an indexing business. And then, by the way, this is n minus I. I should say plus 1. Actually, it's, I guess it's plus or minus L, because I'm going to go from 1, I'll start with, well, let me think about that. I want it to, when I is L, it's going to be 1. When I guess I want to go, actually, you know what? It's just that, xn plus I, because I can get my samples that way. Oh, no, it's I minus 1. That's right, because I want to go from 1 to that. Right, so this gives me W1, W2, W3. I multiply those, and then sum, and I get my Y1. And then I move it over, one sample, W1, W2, W3. I've got, again, my X4. I then multiply, if I do this, multiply, I do my sum here, and I get Y2. And so I just keep on doing this. And I march this guy along. And notice I only have, in this case, L is 3. I only have L weights that applies to Xn signals. So if you will, I have L weights to compute N samples of Y, right? So, and generally L is much, much smaller than N. So there's my weight sharing. Now I know you're saying, okay, but how is this actually sharing weights? Well, we can use matrix notation, right? We can basically embed this within a matrix and actually talk about how this would work. So if I want to, I can have my vector y. So I have my vector y over here. I have a y, 0. Again, habits die hard. I'll do y1, y2, and so on. And then I'll go down to y, and we'll put something in there in just a moment. This is going to equal, well, I've got a w1, w2, w3, all the way to wl. And I got a bunch of zeros. This is going to multiply by x1, x2, x3, all the way down, right? X. Again, this is going to be x of n. That's my n samples. This is my pattern. At the next value, I'm going to put a 0 here and put a W1 here, a W2 there, WL minus 1, WL, and then put zeros. At my next pattern, at Y3, I'm going to put 0, 0, W1. This is going to go WL minus 1, WL, zeros. And so what you can see here is I'm actually generating a matrix where I have this kind of structure, right? This is where the non-zero stuff happens. This is 0, that's 0, that stuff's non-zero, okay? And actually, as it turns out, what we do tends to happen for these types of systems. What we tend to do in neural networks is we tend to kind of truncate rather than zero padding. Signal processing folks would say, I'll just put some zeros at the end, but then that creates some artifacts. So we tend to actually go down and make this work out where this guy's n-dimensional, but then this is actually shorter. So this guy is only y of capital N minus L, I think it's plus 1. Right? So we get basically the number of non-zero samples that are possible. So this tends to be this way. But notice, this guy, this is like my W M of K. That's my weight matrix, right? Generating my outputs, giving my inputs. So this thing would normally be, N, well, be on the order of, right? It's roughly N squared, is approximately N squared in size, but has only L weights. So it's really constrained, right? Incredibly constrained. So, N squared weights, but I only have L weights. So it is the case that I don't have that many degrees of freedom in the system to produce this output. And that's good. And by the way, there's something else that's true. There's also weight sparsity, which means that many elements of WMK are 0. That's also important. It's beyond, it may be hard to try to fill all N squared elements with L values, so I'm going to have to give up some. But in this case, I actually give up a lot. I actually give up roughly half here. And I know you're saying, well, what about in images? This is, by the way, this is what's done in audio signals. This is for audio signals. So, by the way, that's kind of a hint. You guys are actually going to build a neural network to classify some audio signals because it's easier to do the 1D thing. In images, we use 2D convolution. And what's that? Well, that's just, if you will, a set of weights which are two-dimensional. W11, W12, W13, W21, so on, W31 to W33. And now I've got these weights, and they're kind of a pattern that I'm going to drag over my 2D image, right? I've got my pixels in my image. And if you will, X of N is sort of pixels in image. And there is sort of a convolution where I take this and I put it here and I do a weighted combination. And then I put it here, and by the way, that weighted combination would be, if I sum it, would be Y11, kind of the first element. And then I would do this weighted combination here, and that would give me Y12, that image. And I'd get that image by dragging this guy around, doing the weighting and the summing. And again, I only have however many weights in that particular patch to actually adjust for this whole image. So again, highly constrained. Now, I know you're saying, okay, does this actually fit the model? Yes. You can say this is Y of N is equal to W of K times X of N, where this thing has structure. It's a different structure than what I just showed you. It's not a toplet structure as I just showed you. But there is a structure for these weights that will do that will actually compute the output. Actually, I guess I called it Y. I should say it should be D. It's actually D hat of n, k, is going to be this. And then, of course, I have my bias. I have my bias weights. Sometimes the bias weights are actually constant, though. They may not be. It might be a single weight for the entire image as opposed to a bias weight for every value. So it may not necessarily be a vector. But you get the idea. There's actually an additional bias that I have. But basically, I'm able to have a structure in this so that there's sparsity involved, and I'm able to get these outputs. And I know you're saying, well, yeah, okay, I see how this is. This doesn't seem to be too bad. But this is basically for a single image in to produce a single image out. For many structures, we don't do, or a single audio signal in for a single audio signal out. For many systems, we don't do just one-to-one. Sometimes we'll go one input to three outputs. So you might say, well, what if the layer has one input and say 3 outputs? Well, then what it amounts to, if it's a 1D convolution, what it amounts to is I'm going to have, if you will, kind of this thing stacked 3 times, right? My W is going to be something like that, right? With zeros here, 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 and here. And there's going to be, if you will, 1, 2, up to PO outputs. Each one of these, though, is n-dimensional, right? And of course, this was n-dimensional. So I end up producing, if you will, this produces P naught n samples from n input samples, Pn output samples for n input samples, using only, again, and by the way, these are all tied together, using only P naught L coefficients. So again, what you're finding is L is much less than n squared, right? And then you're saying, well, what about if I have multiple inputs, right? What if I have PI inputs and PO outputs? Then guess what? It's the same thing, except now I'm replicating the structure, example, if P naught is 3, P in is 2, then I've got this weight structure which is like this, and I got another one over here, and I got one here. So you get the idea, right? This is, my matrix keeps on getting larger and larger because of my number of my samples, but I have only, if you will, 6 sets. I only have PO times PI times L weights for a matrix which is PI n in and PO n out, right? This is again for my W that I have. So again, it's going to be for for PO outputs. PO n squared outputs. So again, the scaling is basically L, L much less than n squared. So that's the benefit. So I get this weight sharing. Now, you might say, oh yeah, this sounds really fancy and it sounds really modern. And yet, where's the idea? Well, handwritten digit recognition with the backpropagation network. Jan LeCun, Mr. Bozer, Denker, and so on. AT&T Bell Laboratories. This is NIPS, which is Advanced Neural Information Processing Systems 2, November 1989. Okay? You're saying, what do you mean 1989? Well, guess what? They measured the data for the Postal Service. They had data like this. They had things like this. This should look familiar. Kind of the MNIST data set that still is used today. People still using this.
type of idea, they said, you know what? It's really good, we constrain the connections in the first few layers to be local. In addition, if it's useful for one part of the image, it's likely to be useful in other parts of the image, because obviously they're displaced slightly from their position in typical characters and so on. And so we generate feature maps. And so this is a weight sharing technique, but it's already described in the original error backpropagation paper. So go back to the original paper that had error propagation in it. And sure enough, this is also in it. So again, the idea is there. Now, why you're saying, why isn't it that we're doing it? Well, okay. You have to give them credit. This was hard. This was harder, okay? Where is it? So they got 1% error, on the order of what we were just describing. I just showed you the dropout paper. They were talking about 1% error. Let's see. A complete training session, 30 passes through the training set, takes about 3 days on the Sun Spark Station 1. I had one of these, actually, on my desktop. It was a 20 megahertz machine. All right? We've marched up Moore's Law to where 3 days is on the order of about a minute now. Okay? So that's the reason why this was hard. But it's great. They did the training in 3 days, and then they passed it to a DSP, and then they just had the thing compute. And by the way, the DSP recognized things like that, which wasn't in the training set, and it could run 30 classifications, video data rates. Not too bad, right? So basically, the ideas are there. All right, we'll go ahead and stop there. Look for the homework. We will have it up for you, and we will see you next time. Thanks.
수영 세지 마.